Around. Let's get started.
Mä pistin nyt päälle. Se lähtee.
Yes, hyvä. Kiitos. Joo, ihan silleen mä katson tuossa. Mä voin vaihtaa sen siinä kohtaa, kun Fredu.
Joo, ja sen nyt jo pistää.
No joo,
Tai no, pistää sillä tavalla, että siinä näkyy se stage vaikka. Hyvä.
Okay. Hey, welcome to the November Turku AI meetup. I'm sure if you already know, like everybody already knows me, but I'm Otso. I'm one of the common organizers here. And this time we have two amazing talks from Oz and Fredu. And first of all, let's give a big hand to Sami, who organized the location and the beer and the drinks and the food that's going to arrive probably in between the talks. So I'll let Sami say a couple of words about Vaadin, but let's thank him first.
Well, yeah, thank you. Nice to be hosting. First time I'm hosting any meetup here. We have been hosting like Turku Frontend and other local events before, but this seems quite hot topic this time, so let's see. Yeah, like I said, compulsory advertisement from Vaadin, and now we have a problem.
It's called the demo effect.
No, yes, let's see if we can get this one running. Fredu's computer. I blame that, not our setup.
The cheap Apple adapter.
Yes.
Non-Apple adapter.
Yes, let's see. But you probably want to present something here. Are we there? Okay. Yeah, so a couple of words about Vaadin. Who knows about Vaadin? You know the name at least, yeah. Who knows something else? What we do? Fredu knows, yes, I know, and maybe someone else. Okay, yeah, a couple of colleagues. So what we actually do, we do UI components, and they're open source UI components. It's under platform, and you can find them in Vaadin.com. So basically, if you need a web UI, you can find components for that at Vaadin. And here you can see some of those. So widgets like drop-down list, date pickers and such. And then real idea is that they run in the browser, but you can also use them as Java developer on the server side. So there's two ways of using those. Anyway, that's it about what we do. We're based in 3 countries at the moment: Germany, Finland, and US. And if you are a JavaScript developer or Java developer, take a look at the jobs page at Vaadin.com. That's all I wanted to say. They say the AI is the new UI, so let's go to there. Yeah, like you mentioned, the pizzas will come later. So after the first talk from Fredu, we'll have some food for us. Okay, Fredu.
All right.
Go ahead.
Does this mic work?
Yeah. Just turn it on.
Blah, 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 blah. All right. Slight delay, but it works. So hi everyone, my name is Frederick. Hey, familiar faces in the back. So let me see. It works. So the idea was to talk about deep learning challenges. A little bit about the company first, so you know why we are talking about deep learning challenges. Our background comes from, we were the first ones to build the deep learning orchestration and pipeline management for a company called Leap Motion, and that sort of was the idea for starting up the company also. And through that, we've networked a lot with Google, with Uber, and Netflix, and Airbnb back in Silicon Valley. They all have seen these same kind of issues that I'm going to talk about today. So these are sort of generic issues when going into doing deep learning in production. And that brings us to Revelation, actually, also. So deep learning challenges in production. So deep learning is like teenage sex, right? Hey, come on, guys. The more you drink, the funnier my jokes will be.
I don't remember anymore.
Ah, good comeback. So yeah, no, everybody talks about it. Nobody really knows how to do it. Everybody thinks everybody else is doing it, so everybody claims they are doing it too. So that's teenage sex for you, and that's deep learning for you. At least between the big bosses, this is even artificial intelligence and AI for you. For us more professional guys, deep learning today is kind of the same as AI is for the big bosses. So, but the talk about deep learning has changed a bit throughout the years. So if we take a short look into history, the last 20 years or so, if we look at the beginning of the 2000s, people were asking that, can it be applied? Can we even use deep learning in some sense? Then in 2010, 2015, people asked that, what can we apply it on? And then today, companies are asking more that, how do we make it core business? How do we make it drive our business? You know, everybody's talking about AI first or machine learning first, sort of the company is very data driven, that it makes decisions based on data. So now companies have realized that, okay, machine learning and deep learning in particular is a way to make companies make decisions, not only see the data or analyze the data or visualize the data and stuff like that. And this is the big player. So every big player in the Silicon Valley, for instance, is betting on this. From Google, from Uber, to Lyft, to Netflix, to Airbnb, they all see that deep learning is the way to drive the business. It's not a side track of the company. So you've seen these examples like self-driving cars, recommendation engines, NLPs, or image recognition, or chatbots. They're all sort of deep learning driven in some sense. But there's a difference between doing deep learning experimentation and doing it in production. So if you're starting out on your deep learning journey, you're probably going to start from your own local laptop here. And you're probably going to start with some files, maybe some image recognition stuff on your own computer. And a good way to start with all the online courses start from the same thing. They're using Jupyter Notebook to do these experimentations in the cloud. How many here have used Jupyter Notebooks? Yeah, so sort of a nice web UI where you can actually write some Python code, you can run it, you can see some results, you can write something again, you can see your results again. You can explore and get to know the model or get to know the data and build some preliminary models on it. But when you go into actual production, so as an example, if you think about your Jupyter Notebooks here, usually you run it so that you run cell 1 first, then cell 2, then cell 3. Cell 3 probably is depending on cell 2's results. What if you run them in the wrong order? It's not really maintainable or shareable between different teammates when you start doing something production ready that you actually want to redo and you want to share with your friends. So what is then production scale deep learning? Well, usually it's large amounts of data. So it's hundreds of terabytes of data that you build the CNN on for image recognition, for instance. And it usually requires a lot of processing power. Your own laptop won't be enough anymore to actually build those or train those neural networks. And you need at least some kind of knowledge of what you're doing, as opposed to maybe maybe we should have included that guy on the previous slide also. You need some knowledge when you're doing experimentation as well. But these are the three things, and I mean, we probably all agree that companies have a lot of data nowadays. I mean, all new startups are built on the idea that you're gathering a lot of data so that you can make something with the data. No matter what we're going to do with the data, we need the fucking data. And we all have processing power today. Like traditional companies have big server farms, or everybody has access to AWS or Azure or Google Cloud. And there's a lot of sort of intelligent people in data science coming from software engineering, coming from an analyst background or academic background or anything at all. So there's people as well. But talking with these big players, their largest challenge is not data, it's not processing power, it's actually, of these three, it's actually finding the right people. You can see this if you compare in Silicon Valley salaries. If you go to glassdoor.com and compare software engineer salaries to data scientist salaries today are 30% higher than software engineer salaries. And I mean, it's not because they are better or anything. There's a big demand for it. There aren't as many people who are experienced in doing machine learning or deep learning. So talking to these big companies then, how do they compete in this? So they have the data, they have the processing power, and they have, to some degree at least, the people. So there's 4 things for fastly doing something with deep learning. The first one is experiment reproducibility. Oops, I'm standing in front of it. So experiment reproducibility, this basic scientific stuff that you should be able to do the same experiment on and on again. You should know how you did it previously. The second one is regulatory compliance. There's regulations about stuff we've all seen GDPR in the last half year. Healthcare has its own regulations. Autonomous driving has its own regulations. Everything has their regulations. You have to comply with it. And there's more compliance rules in AI and deep learning coming up once it gets more known. Then, because people are switching jobs, because they're tempted by higher salaries or bigger companies or nicer jobs, we need to onboard people quickly. We need to get them productive quickly, and we need to know what the previous people did that actually left the company as well. And we need a fast way to do quick experiments. So if we think of these 4, these are what the big players are thinking about, and it's not only the big players in Silicon Valley, it's the same with any companies in Finland or Sweden or Germany or wherever as well. When you're doing deep learning for real in production, not only experimenting, these are the things that matter. From a single data scientist point of view, the one on the edges are probably the most interesting ones. You're interested in getting quick experiments. You want to try something out, fail fast, and get better and better and better results. You don't want to wait for your results 80% of the day. You want to try something and you want to get results quickly. I mean, it's not very motivating for just drinking coffee and waiting for the cloud machine to compute something ready. Or for some, it might be. Then experiment reproducibility, so that if you're a team of, say, even 2 people, you should be able to know what the other guy did. On Monday morning, it would be nice to know that what I did on Friday as well. Usually I have this problem, but I don't know about you. So if we look at these 4 things one at a time, if we start from experiment reproducibility, how many of you heard about Uber's self-driving car driving over a person like half a year ago? Yeah. So if we were to look at Uber's this case where the person got under the car, if we were not able to go back and see that how did this happen, how could we improve it? I mean, was there a bias against slow people moving over pedestrian walkways? I don't know. There might be sort of a bias somewhere. And then how did we train the model? What was the data that we used to train the model? And which model was it that resulted in this? There's probably a chain of different models that resulted in this. And at the same time, how did we train the model? What was the algorithm that we used? In Uber's case, Uber is famous for their Michelangelo framework that does this kind of stuff, that does the orchestration and keeps track of what's been done. So they were probably able to find out what the challenge there was. But if we look at the experiment in general, like a machine learning experiment or a deep learning experiment, usually you have your input, then you execute it somehow, and you get an output. And then you iterate over and over again in order to get a better output, a better model, so to speak. So the input is usually like your code. Then you have your parameters, your hyperparameters, and your data set, your training set, and your test set, for instance. Your training code, you probably have it in Git or Bitbucket. Your hyperparameters usually go as input to the training code that, yeah, these are the parameters that I want to tune when I'm training my model, and the data set comes as input to the training code as well. Then you're going to execute it somewhere. You're going to run it on some physical hardware. It can be on-premise hardware. It could be your own machine. It might take you 3 months to get the result compared to put it on a more powerful cluster of GPUs in AWS. But still, it could be anything. The environment, what version of Python am I using? What version of TensorFlow am I using? And it's going to cost you something, be it then in minutes in your local on-premises hardware, or it could be like physical dollars from a cloud provider. And then you're going to get a model. You're going to get a model. There are the weights or the biases and the network configuration, log files of how you actually did the run, results from the run, and it's the statistics there under the picture. So statistics of how it's been trained or how it's performing. So this is an experiment. Sadly, however, in many cases of companies starting up with deep learning, they don't really sort of keep track of all of these. Of course, the code, I mean, we have all done some software engineering. We have it somewhere, right? Except, I mean, if you're doing something with a notebook on your own machine, it's probably a file on your local desktop that says best model so far 43 and best model so far 86 and so forth. But I mean, you have some kind of version control at least. And the model that's in production, at least that's somewhere deployed. And hopefully you have your previous models somewhere as well. But this is quite a big challenge. I mean, there's quite a lot of data lost here of how we derived the model. Imagine if Uber did not have track of what were the hyperparameters we used to train this model. Maybe they did a grid search of 1,000 different hyperparameter combinations and arrived at some model. Which one was the one that we selected? Or what was the training data? If we wouldn't know that, or which hardware did we use? Did we use a CPU or a GPU? Did we use which version of TensorFlow and so forth? So that's one of the big challenges in deep learning that all of these big companies are struggling with. Then we have regulatory compliance. You can fall asleep now for the next 5 minutes if you want to. I know everybody's really interested in regulatory compliance. How many of you have heard about this before? Yes, spoiler alert, it's GDPR, our own favorite child. So what does anybody here know what GDPR says about machine learning or deep learning? Otso knows, but he's seen the slides before. Yeah, you know as well. So GDPR simply says 3 things. An individual must be aware of automatic decision making. Okay, you have to tell somebody that this decision was made by a machine. Simple and easy to say. Well, the individual must have the right to gain information about the logic behind the machine learning model. So you have to tell them that how did my machine make a decision? If you make a claim to an insurance company, how did the person make a decision that if you got your claim or not? I mean, it's quite hard to explain even how a person makes a decision. He probably makes a different decision based on if he or she had lunch before she made the decision or not. It might affect it. But I mean, it's quite hard to explain it. At least in machine learning models, it makes the same decision every time based with the same input. But we have to explain that somehow. And the third one is that the person is able to deny the usage of automated decision making. But I'd like to get your attention for point number 2. That's probably the most relevant here. That you have to explain it somehow. There's different ways, more and less scientific ways of showing how a machine learning model makes its decision. You can visualize the output based on different inputs. You can try to visualize how the neural network has, if you're looking at the image, what it sees at different layers and so forth. But the most important thing is that you have to know how the model was trained so that you can actually test out these things. Again, we come back to the same fact that you have to have some kind of version control of how the model was trained. Okay, we ticked 2 things off the list already. Then fast onboarding of teams. So if we think of the machine learning pipeline, and when we talk about the machine learning pipeline, we talk about going from left to right here. We start from data storage and exploration. We go to extraction of data, transforming the data, pre-processing the data some way. Then we're going to actually building the model, training it, optimizing it. Then we deploy the model somewhere, and then we have it in production. So if we look at this and think about how effective are people that join our project, look at the different sort of tools that we have here. So in the data storage phase, we have different tools. We have like SQL databases, we have RStudio, we have Excel sheets, and so forth. Then we probably have some scripts that transform the data, that do the extraction from the databases, transform them, and pre-processes them. Then we have some frameworks that actually we train the model with. And then we deploy it somewhere, maybe in the cloud, maybe in an edge device somewhere, but we want to deploy it somewhere. And then we want to monitor it in production, maybe just raw log files, or maybe we have New Relic or something else that we use to monitor the models. So this is quite a lot for data scientists. I mean, it's quite a lot for software engineers already to know about how to set up a cloud instance in production and how to monitor it compared to how to do SQL queries. So all of this for software engineers a lot. Think about data. You as data scientists, you might have different backgrounds as well. Some of you are from software development. Some of you are from maybe a more mathematical background, analyst background, and so forth. Usually we have different teams, so we have data engineers that help us along, we have IT departments that help along on the way, but at the end of the day it's quite a mismatch of non-integrated teams and non-integrated technologies that you have to master in order to get something trained. So these big players have solved this, or at least attempt to solve this in some way. So the most famous one is probably Uber's Michelangelo framework. If you Google for that, you can find the most information. Airbnb has their Big Head framework, Netflix has their own, Facebook has their own, Google has their own, basically orchestrating all this kind of stuff. The common denominator for all of these is that they are proprietary for them internally. They are not open to the general public, so you can't use them. Some parts here and there they've made public maybe and are plans to make even more public, but they've seen these challenges, they want to solve these problems internally, and necessarily not I don't know, I'm just guessing, but Uber might not want to open source or make it available because then Lyft would get a head start. If Uber's competitive advantage is that they are able to train more neural network faster than Lyft, then surely they don't want Lyft to have the same advantage as well. They invest a lot of time into being able to do this. Google did a study in 2015. They released it at the NIPS conference. You can find it here. You can just type in that in your mobile phone. They did a study of how much of their internal data scientist team's time went into actual machine learning code and how much went into configuration, data collection, data verification, machine resource management, and serving infrastructure. And they came out to this picture is actually from their paper, but it says 5%. I don't know if it's actually, this is 5% of the graph, but 5% of their internal time went into actual machine learning task. 95% went into everything that surrounds it. And they saw this as a problem. Today, they're a lot ahead of this. Probably around 50% goes into machine learning code, but still they've been able to solve it at least to some degree in the last 3 or 4 years now. Then the last point is quick experiments. So here, how many of you have a software development background here? How many do not have a software development background? Okay, so I'm going to draw an analogy from the software side here. So if we think about 1998, I wrote my first code in the beginning of the 1990s. My first sort of real projects were in the beginning of the 2000s, around this time. So if we think about what we can learn from software engineering, during this time we deployed stuff 4 times per year. We had these version clocks that you can deploy in March, June, September, and January or December or something like that. And every time you deployed something, everything broke down. I mean, we had these big Kekkos commits where everything went out on the same day, and we tested it for 1 month when nobody was able to touch any code, and we deployed it then. Today, companies are deploying new stuff 10 times per day even, and virtually nothing breaks today. And how is this possible? I mean, there's, of course, we've been able to crunch stuff into smaller pieces, agile methodologies and Scrum and stuff like that. But tools have helped a lot on the way. So we have version control today in software engineering. We have continuous integration. We have microservices. We're making stuff in smaller pieces. We have cloud computing, so we don't have to understand how the servers work and every part works. And this is something that we could learn from in deep learning as well. Sadly, we're more in the 98s than actual 2018s in deep learning today. There aren't any standardized big tools or continuous integration, microservice or cloud computing. These are all being worked on and solved at the moment, but none of them are there yet. And this slows us down a lot. So these are the 4 recipes for fast return on investments, fast deploying into production, especially in deep learning. So now shortly, I will very suddenly slip in some advertisements about Valohai as well. So what is Valohai and what do we do and what does this have to do with anything that I've talked about so far? So we want to take you from this picture to this, oops, come on. Oh, come on. From this picture to this picture, so everything is automatically version controlled. You don't have to explicitly take version control snapshots of every training run. Everything is version controlled. We want to take you from this picture to this picture, have orchestrated pipelines, just like these big company internal tools are doing. Do it for all of your pipelines so you can automate stuff that when there's 20% new data, let's kick off an extraction that does something to the images, then train a new model, do hyperparameter sweeps, select the best model, put that into a test environment, test your software against that automatically. When it passes the test, deploy it into production and start monitoring it. So that you wouldn't have to have 5 people doing it and doing it manually all the time. The other part is we obviously want to take you from this picture to this picture as well. So actually, so that you spend your time on machine learning stuff, not the stuff that you shouldn't spend time on, that sort of infrastructure and non-interesting stuff. So we do reproducibility through version control, so that you can reproduce. You can go back and see, how did I do this previously? Regulatory compliance through 100% audit trail. You can always describe that. How did my model get trained? And from there you can use some more or less scientific methods. There's lots of methods for describing how your model behaves, but they all depend on the fact that you can have version control for your data or your entire model. Fast onboarding through a common way of working. Everybody works in the same way. You have managed pipelines. And quick experimentation through machine orchestration so that you don't have to do stuff by yourself. And so that this isn't only speak, I'm just going to give you a quick demo actually now. So how many of you are familiar with TensorFlow from before? All right. So I have a small TensorFlow example here. This is available in GitHub, Valohai/TensorFlow example. So this one here is basically 2 pipeline steps. We have batch feature extraction.py. That feature extracts we're using the MNIST data set here. How many of you are familiar with the MNIST? So MNIST is handwritten digits, like people have written by hand something, and then we're trying to train a neural network to recognize, is this a 4 or a 5 or a 7 or something? So first we're pre-processing those images in some way. Then we're actually training the model. Then we have some utilities packages that both of them are using. And then we have a Valohai YAML file. And in this YAML file here, we have defined these pipeline steps, like batch feature extraction, train model. We have defined that whenever we run this step, we're going to use this Docker container. How many of you are familiar with Docker? Maybe half. So Docker is a way to encapsulate that these are the libraries that I have here. It's basically a virtual Linux. So you know that, okay, it has this Python version, this TensorFlow version, and this C version, GCC version, and so forth. So we want to always run it in the same environment so that we know what it's run on. Then we give some input to it. Same thing with the train model again. We bind it to a container, and we give some hyperparameters that we can tweak. So if this is my code now, so I have this in GitHub here. I'm going to import this into Valohai, create a new project. So Turku AI demo. So I'm going to go quickly here and just import this project here, save. It fetches the YAML file, and then I can get started. So let's create an execution. So execution being one step of the pipeline here. The beauty with everything I'm showing you here is on the web UI here, but everything you see can be accessed through an API or a command line as well. So I'm going to first select here that where do I want to run it. So this is the machine orchestration for you. So do I want to run it on AWS, some instance, or in Google Cloud, or in Azure, or do I as a company have a private on-premises hardware somewhere? We support all of that. So I'm just going to select the cheapest and smallest AWS instance. Which version of my code do I want to run, and which pipeline steps? So batch feature extraction is what I want to run. I can overwrite the stuff that I showed you in the YAML file, so I overwrite which Docker container, but I'll just go with the defaults. Here's some input data that we have somewhere. I'm going to create an execution. It creates it. So what Valohai does for you here is it launches the AWS server, inserts the Docker container inside of it with all, basically the virtual Linux machine is there inside now. Then it goes and fetches my code, and when it has fetched the code, it starts running it. So now my code starts outputting here 25% done, 50%, 75, 100%. And when my code is ready, my code here puts it in an output folder. So we can look at this one here. We can say, okay, from this step we got some images, test labels, training images, train labels. And it's all version controlled, so if I want to go back and see later that how did I get those outputs, I can see that, okay, it was trained in this AWS instance with this code version on this Docker container with this input data. It took me 22 seconds to run it. Here is the log for everything. I can go back here 3 years from now and see it here, and I can write notes and so forth. So then the next step of the pipeline, so we have the images. Let's now train a neural network to actually recognize that. So again, I can select the same stuff here. I'll go with the cheapest and smallest Amazon instance. Well, let's go and train the model. So I can go here and instead of using the data here by default, I can go and see that, okay, here's the one that we trained, uploaded a minute ago. Let's use that training image, training labels, and same thing with the test images and test labels. And then I can go and change the hyperparameters here. For instance, let's go with 900. So I can change the defaults here if I want to. So these are the inputs to my script that I'm going to run. And when I start it up again, Valohai goes and automatically sets up the AWS instance for it, installs the Docker container, and installs the code, starts running the code there. Already going to AWS console and starting a new AWS instance. Those of you who have done it, you know that it takes you like 5 minutes for AWS to start up. After that, you have to SSH into the AWS instance. You have to install Docker, which takes you even more minutes. And after that, you go and fetch your code, and then you can start running this. Now we're running this here in a few seconds. We changed it to, I think we were 700, 900 steps, so it's going to go on for a while. But we can go here and visualize this even in real time, so we can see how the accuracy of our model improves over time. So we can see that, okay, we are at 96% accurate network at the moment. And once it's done, my script is going to, so it was 900, so it's going to upload the weights and the biases of the neural network to the output folder, and I can go and do whatever I want with this. Then I can deploy it to an webcam somewhere, or I can deploy it to the cloud, or I can deploy it to my iPhone or wherever I want to deploy it. And then 3 years later, I can come back here again and see that, okay, this trained model here that we have in production today, it was trained with this training data, with this code, on this hardware, on this software environment, with these libraries, and everything is reproducible, and these hyperparameters here. How many of you have done some more deep learning? How many of you know what hyperparameter sweeps are, or grid searches of hyperparameters? Yeah. So that's usually a challenge, and if you go on your local machine and try it out, then usually you're gonna maybe go in a loop, or maybe you write something yourself so you can do several at the same time. In Valohai, this is the last thing I'm gonna show you, then I'm done. Hopefully, I'm just warming you up for the pizza. So I can do the same thing here. So let's train a model. go with the default data, but actually instead of going with these step size here, I'm going to go with a linear approach from 300 to 800 with step size 100. So it gives you 3, 4, 5, 6, 7. I'm going to do a multiple learning rate test with these 3 values, which gives me 18 different executions. Oh, you can see it, but the sum is there at the bottom right-hand corner. It gives me 18 different, a combination of all these is 18 combinations. So I can just click here, create a task, and Valohai will launch up the 18 machines at the same time, except I'm in a demo environment, so 5 machines at the same time, and then the next 5 machines, and 5 machines, and 5 machines. But still, in theory, we can launch 100 machines at the same time. And that's sort of nice, because when we're using cloud instances, 18 times 1 minute costs the same as 18 minutes. But I'd rather have my results in 1 minute than 18 minutes. So I don't have to wait 18 minutes. I can just wait 1 minute and get all the results at the same time. So the color coding here goes that blue means that the machines are running, green means that it's done. So I can go and look at machine number 7 at the moment. We'll see the same log files here that's running here. It's apparently be completed in 26 seconds, so it's ready soon. And when it turns green, I can go ahead and have a look at it. Let me wait for the machine to actually shut down. So Valohai, what it does, it shuts down the machines automatically, so it doesn't stay running for you by accident. So I can go here, just Otso is going to kick me out of the room soon, so I'm going to be quick. Not at all. So accuracy, if I sort by accuracy, I can go and see, for instance, that, okay, training model number 7 seems to be the best. If I'm going to select my model by accuracy, 96% is the best model of these 4 that I've run, 5 that I've run so far, with step size 400, learning rate 1001, and so forth. Then I can go ahead and deploy it here behind the HTTP endpoint and so forth. So you hopefully got a basic idea of what we do. This is basically the same thing that all the big players have built for themselves as well. In order to be more efficient at data scientists, they don't have to manage the machines, they don't have to know what the team has been doing previously, they don't have to remember what I did on Friday when I come back on Monday and so forth. So just a reminder, deep learning is like teenage sex. If you remember something, you remember that. When you're done experimenting alone at home, protect yourself from surprises and write down who you've done it with. Basic same idea applies here as well. It might take you a while to work around this. It took me a while to come up with this as well. Yes. Me and Otso are here from Valohai, so you can come and talk to us later as well. But I'll give it up for the next guy and the pizza hopefully soon. Thank you. Yes, ask questions.
Let's give a big hand to Freddie and then let's take Carlos.
Yes.
What is the whole process for the part of your
This was the whole process in this example. You might have much more advanced process. We have customers who are, for instance, generating data, so that might be one. So first you might extract some data.
Before part, that how much you have that available?
How do you mean? Come again.
Just about data generating and handling.
Yeah, so Valohai is more about the orchestration part. So you, of course, have to write yourself how you're going to train it, how you're going to extract the data, how you're going to generate the data. But you can hook them together with Valohai, so you can do them automatically step after each other. So that's the idea. But you of course, have to write it yourself. And Valohai supports, of course, any kind of programming language that runs on Linux and so forth. So it doesn't tie you to anything specific. So we have customers who are generating data with C code, who are training their model with Python and so forth. So yes, Pontus.
So deep learning is sort of not the only kind of machine learning. Often use sort of simpler models, but perhaps more different kinds of models. Try to evaluate them against each other. So would you say that Valohai also could support for this kind of work?
Yes. So the example I had is a deep learning. So the question was that can we do other things than deep learning, and can we sort of try different model configurations and so forth as well. So yes, my example is deep learning because it's easier, or it's easier to explain it that way, and it's more sort of data intensive, but you can definitely use traditional machine learning. You can give any inputs to your scripts, and you can have different scripts competing against. If you're talking about like hyperparameter sweeps, then hyperparameters don't have to be integers. They can be strings that just you give to your script, and it then defines the configuration of the model or uses a different linear regression versus something else depending on the input. Did that answer your question? Or?
Yeah, very much.
Okay. Yes.
Framework like this we use in the scientific community. Maybe could you, with this kind of a tool, like share scripts or share data on the scripts one without actually trusting the other party? Like you could, maybe I could run my script on your data without actually seeing your data. Just like
In theory, yes. Yes. So the question was that could you use in the scientific community, like somebody owns the data, somebody else owns the script, and so forth. Then yeah, absolutely, absolutely. Not, I mean, as long as it's accessible by the one that does it, and so we don't have any blockchains here for like checking that if you're doing something, but yeah, absolutely. If you have access to it, it doesn't matter. We support private clouds, or we like private buckets of data or public buckets of data, as well as like private repos of code and public repos of code. So both are doable. Scientific wise, we actually have a valohai.com/pricing. So if you're working in science, there's apply for a free professional account. So research and education licenses are available. So if you're working in that, you can just fill in the form and you will get some free credits, and you will get you don't have to pay anything for using it. So.
If you're interested in cases like that where the data, for example, isn't available to be visible, you wouldn't want to have direct access to everything. You should look into what OpenMind is working on. They're doing a lot of stuff with, for example, federated learning. So I could give you my model, you train it with your data, and then give it back to me.
Any other questions? Yes.
Could you hook this up with the CSC GPU customer?
We could.
Is it possible?
Yes. I don't know if Otso wants to add something.
No, we can discuss it later.
Yeah. Yeah. I mean, we don't have any. The only thing we need for the machines that we're orchestrating need to be some Linux machines that we can add a small agent to that actually we can call. But it can be any. It can be your own machine that's running in your basement even. So there's nothing like that that restricts us. Any other questions? Yes, Pontus.
One more. Can you install your own Valohai instance in your basement? So that
Yes, you can.
read your
Then you have to talk to our sales guys, but that's sort of tailored pricing, but yes. And then you have to swear that you don't try to decompile it or try to just copy it and stuff. Yes.
thank you, Fred.
Thank you.
So next we are going to have some pizza. So let's keep a 15-minute break, eat some pizza, have more drinks, and then let's continue with those after that.
I think I'll just keep it here for a while.
Yeah.
Great, thanks.
Oh, was Fred keeping the mic off the whole time?
niistä niin kuin AI-kehittäjien, miten heidän eksplosyyttä. Eettisiä toimintatapoja voidaan tukea, mitkä on ne ratkaisut. Se menee niin kuin developer-kulttuuriin ja niin kuin aika laajasti. Toi on aika, mä tykkään tosi, siinä on hyvin niin kuin käytännöllinen näkökulma ja sitten taas jos menee niin ihan propellin hattuun teoreettisiin hommiin, niin siellä on semmoinen jenkki-filosofi Jowski argumentoinut sen, jos oletetaan joku negatiivinen lopputulema joskus kauan tulevaisuudessa, niin se ei ole myöskään regulaatiolla selvitettävä asia, vaan se tulee sieltä koodarien, moraalin ja eettisyyden kautta. Niin, kyllä. Viime viikolla meillä oli, se oli ihan hauska Itä-Asia. Joo. Se oli hauska. 3 aasialaista proffaa. Kyllä japanilaisen ja korealaisen kanssa tuli helpommin oli sama linja kuin sitten taas kiinalaisen kanssa oli ehkä erilaista näkemystä, mitä etiikka tarkoittaa. Mutta tämmöinen dialogi, en mä ole mikään kansainvälistä suhteiden ihminen, mutta tämmöinen keskusteluyhteyden säilyttäminen on varmaan kuitenkin tärkeää.
it on before we start.
Yeah.
Have you been doing a lot of talking?
Yeah, quite a lot nowadays.
Oh, yeah, oh, okay, but you have that.
I have this actually. Maybe I should move a bit up. Yeah? Or no?
You can talk at your
How is
voice
it?
there.
I don't think so. Even upper? Here? Maybe not.
You're bared.
Yeah, maybe.
I think it's going to be fine.
Yeah.
Okay, please gather around for the second talk. We can get started. Okay, so the second talk is going to be from Oz from Top Data Science. Without further ado, let's give him the floor.
Hello everyone. Every male above the age 60 will have some cancerous cells in their prostate. That was my talk, thank you. No. So this is a rather dream topic. So it's a nice evening. So cancer, it's not nice topic, right? So, but hopefully I will talk about the solution to diagnosis of this thing. My name is Oğuz. My full name is Oğuzhan. I'm one of the 3 co-founders of Top Data Science, and I'm leading the AI team right now. My background is machine learning research. So I was doing research on deep learning when nobody cared, but now it's quite hot topic. So that's why we are here all together. Thank you for your time. So today I'll be talking about one of our solutions for detect diagnosis of cancer. Quickly about us. We are a company called Top Data Science. We are a Helsinki-based AI startup. Actually, as of today, we have been selected in the top 15 startups in Finland and top 5 in AI consultancy with Dying Studios, Fourkind, Head AI, Silo AI, and here's us. So what we do is actually AI as a service. So we are not a single product company. Let's say we are really good at solving problems with machine learning, and our clients are good at, well, having problems. So it has been a good match. As I told you, my background is machine learning research. I am now in industry in my own startup, but I still do some research because it's fun. So yesterday I just published this paper using deep learning. I was able to predict flu in Finland from Instagram images and text. So you can check the paper. It's of course open. So I mined thousands of, let's say, images and whatnot from Instagram, and I was able to predict. You see, this is the prediction of flu, official weekly flu counts in Finland. So this kind of cool stuff, I'm just giving an example what deep learning can do nowadays. But let's go to our topic, which is cancer. In our company, we don't do only healthcare, as I told you. So we have big clients like GE, which we do AI for them. We have Stora Enso, we predict how their factory behaves, and we do lots of image recognition for a Japanese company. So more than half of our revenue comes from abroad, actually. The problem statement, prostate cancer. It's one of the most prevalent cancer in males in pretty much in any country, including Finland. The thing is that it's really heterogeneous disease, so having some cancer in your prostate, cancerous cells, it doesn't mean you are gonna die. It can be totally harmless or totally lethal, so this makes the problem quite difficult. And the primary risk factors include age, as every other cancer, so we as species are privileged to live long. Then the downside is that there's no free lunch. You get these kind of weird diseases like dementia or cancer. And obesity is one of the other factors. The only clinically valid diagnosis for prostate cancer is that it's a biopsy. Biopsy means they take a tissue out of your prostate. You should be thankful that I'm not going into details of prostate biopsy and in this nice evening, but it's a nasty process and we don't want that. It's really obtrusive. It's not fun to be in that, right? So basically they take a tissue, and the problem is that the best, which is ultra-guide sounded biopsy, it has a hit rate of 50%. So it may or may not hit the cancerous region. It's a coin toss. So meaning that in your lifetime as a male, you most likely go through this biopsy several times. Well, the expected value is 2 statistically. Okay, so the diagnosis, clinical diagnosis, it's called Gleason score. The pathologist looks under your tissue for hours under the microscope, and he or she checks the appearance of the cell morphology and gives a score, 2 being it's benign and you are fine, and 10 is pretty bad, let's say. So the trick with this Gleason score is that 3 plus 4 is not clinically the same as 4 plus 3, right? So there's a difference. So where does AI come in here? So this is the problem. This image is gigapixel level. One image is 20 gigabytes. You can't even open it in your laptop or whatever. So it's super resolution image. So you can zoom in forever like one of those CSI movies. Like it goes on and on and on, right? So, and you are trying to, or the pathologist is trying to detect these kind of regions in this gigapixel level. It's really tiring. It's really fatiguing. People get tired, people miss. Pathologists and radiologists don't have enough time. They have lots of stuff to do. Can we automate or at least semi-automate this with machine learning? Yes. So we are collaborating with Helsinki University Hospital. We have data from more than 300 patients. So this data is basically consisting of 12 to 15 slides, meaning that a prostate is removed from the patient and literally someone slices it just like an apple, and you have 12 to 15 slides of this, and then you scan it in this super resolution. So you have a digital image. One image is this resolution I don't even want to pronounce. So it's a huge image, right? So and one single image, and you have this multiplied by this many. One image is like 20 gigabytes or something. Yes, please.
Can you remove prostate, or is it like a dead person?
So basically, that's kind of the last thing you do. No, it's not.
I mean, these patients, are they dead or?
Some of them. By now, because it's a retrospective study, we look back retrospectively. Yeah. But this doesn't have to, the solution, it doesn't have to be prostatectomy, so you can use this AI in the biopsy when you take a tissue too, so because that's the same tissue, right? And the data is pseudonymized from the Helsinki University Hospital side, meaning that we don't know the patient identifier, of course. Our pathologists have been working with us. We provided them tools to annotate the data, so basically they have been annotating the regions where inside this cancer for hours and for days and days. So this is a continuing project, actually. So we have pixel level annotations of these huge, huge images. A typical annotation is like that, and if you zoom in, so this is the cancerous cell, for example. Let's talk about our machine learning approach, deep learning approach specifically. So you can't feed into a, let's say, fully convolutional net, or let's say UNet, like it's called segmentation, because you have the mask already. You can technically do segmentation, but not in this case, because this is such a huge image that you can't just feed this image to a convolutional neural net or something. So we first get the binary mask out of it, and simply we do windowing, right? We literally window this image into tiles. This is just an example tile size, 256 pixels, but of course we try many different tile sizes. And we sample from cancerous regions and non-cancerous regions these kind of square tiles. So it's a binary classification problem instead of segmentation. Segmentation means you give an image and the convolutional neural net generally outputs the contours. But we turn this problem into a classification problem because of the reason I just mentioned. Then we feed into a quite fancy architecture. I will not go into the details. With different tiles are like feeded into into different branches and then concatenated, and actually even in a 3D structure, so 3D column nets and stuff like that, to get a probability of that specific region having a cancer or not, right? So it's the output is between 0 and 1. It's a continuous number. Okay, bear with me if you are non-technical, but I have like 2 slides about a couple of mathematics stuff for people like me. So neural network training is a non-convex optimization because there's no interesting problem in the world that is a convex optimization, because you can find it like that, right? So non-convex optimization means how to put an analogy. Let's say you are in a golf field, it's dark, like huge golf field at night, and you are here and you have a torch or a flashlight, and you can only see 5 meters around, and your goal is to find the lowest point in the golf field, which has lots of ups and downs. So the best thing you can do, okay, this goes down, let's walk there. Then you keep searching and stuff. Then at some point you go to this point that it is really kind of, there's everywhere is uphill, so you are in a minima, and you just hope you are in a global minima. Global means the minimum point of the golf field, but that mathematically never ever happens. So you are in a local minima. This is a non-convex optimization, yeah? You are trying to find a minimum point of an error field. And in high dimensions means when your neural network is really big, which it should be if you have lots of data. The main problem is not this local minima, but the saddle points. Saddle points, mathematically, it means it's a minima in one dimension and it's a maxima in other dimension. So this is an interesting finding by this paper by Dauphin. So it's published in NIPS. NIPS is, if you are familiar, it's like Olympics of machine learning with CVPR and ICML, I would say. These 3 conferences are like, if you publish something in NIPS or CVPR, you probably know what you are talking about because the acceptance rate is so low. So the paper has this mathematical actually foundation explaining that the ratio of number of saddle points to local minima increases exponentially with dimensionality. I will explain what this means. It means this is your training curve, so this can be iterations or number of hours you train. This is a typical training. This is error, so you want it lower, so it's learning, your error is decreasing. Typically, you would think you would stop your training here because you think it learned, but it's actually, if you have a large network, it's a saddle point, so you get stuck here. If you wait long enough, you will continue dropping down, right? This is a trick. If you are working with millions of images and a huge network, let's say 100 layer deep, something like that. So you go down and end up in another saddle point, and you go down. So this is what it means in this sentence in the paper. So if you are training a large deep net, don't early stop, yeah? Second finding of this interesting paper is that, why am I explaining this paper? Because we are using these mathematics behind our solution. The probability of a point being a local minimum, but not a global minimum, increases as the loss function gets closer. What does it mean in common terms? You are statistically better off training a large network as long as you don't overfit. So fit as large network as possible. And if you end up in a local minima, which you will, it's okay. It's as good as a global minima if your network is really large, yeah? We can talk about mathematics afterwards if you're interested. So that was the maths. How we do validation? So we train, of course, with hundreds of thousands of images, and we leave some patients out for validation, right? Then we simply do the same tiling, windowing, pass through our model and get a probability. And yeah, there is a heat map exactly showing pretty much this part is red and this part is red. So right now, it's basically covered by my picture, but the point is that we are reaching state-of-the-art accuracies. Accuracy is not the metric here, because if I say 90%, no one will get cancer here. I'm probably right, 99%, hopefully 100%. So clinically, accuracy, it doesn't matter, but area under the ROC curve is the metric, and we are getting state-of-the-art results. I will not share the exact number because we are now publishing. I can send it once we publish it. We are writing the publication. I can show the video how it kind of works. This is me talking, but if we continue. Yeah, so basically, this is a histopathology, a tissue image, and these are the regions highlighted by our AI. So we have this tool now, right? And it can be used in a microscope if you integrate it, or you can set it up in a survey in a hospital, and instead of pathologists looking at images for hours, they just put their data in a folder using Valohai. And basically you can run your training or even inference there, so that things are very much automated. We have our in-house GPUs. We sometimes use, of course, for some projects, AWS too, but for this project, for security reasons, we want to keep our secure workstations. We have several GPUs in Helsinki. Let's talk about the value. So of course you save enormous amount of time. You means the whole healthcare pipeline, or the pathologist, or the hospital. And the detection is as good as a single human being, professional pathologist, because we train our algorithm from annotations from several pathologists. And this can be helped also in training junior pathologists, right? And for the patient, as your biopsy is more accurate, you will most likely get less biopsy, so that's the value for the patient. And from the business side side, what has been the key enablers? First of all, constant communication with the client, which is clinicians and doctors and a hospital, because we are a bunch of nerds. We have zero medical knowledge whatsoever. So they have to explain what is going on. What is cancer? I don't know. So what is like a clinically relevant, clinically acceptable accuracy? So these kind of things. So like some big companies, they claim like, let's give us the data and you will get meaningful results. It doesn't work like that. I wish it worked like that. So you have to be constantly talking with the field experts, whatever that field is. It can be paper production. You have to talk to that guy who's been in that factory 30 years. There's no other way you're going to solve that problem. He knows more than anyone in the world. And you have to talk to the doctors. So it's not only a coding thing when it comes to the business. And it's always good not to sell snake oil. You shouldn't overpromise. again, like some companies, you shouldn't, let's say, overpromise in a way that claim big stuff and hoping you will get those stuff, because you are both actually damaging your own business and reputation, but as well as the whole machine learning and AI field, because then people are skeptical. Is it like a balloon? Provide easy to use annotation tools, or in general tools for your clients, because they have lots of stuff to do. They don't want to cooperate with you if you don't help them. Help them to help you. Of course, use open source tools like TensorFlow, which has been our backbone, and explain them how this works, because they have been explaining you the medical knowledge. So knowledge transfer, this is not specific to this project. We do lots of AI consulting. So knowledge transfer is very important. Many clients, they want to know how your model works and why it outputs those stuff. And if anyone claims nowadays deep learning is black box, he is apparently not following the recent research, because last 2 years, and 2 years is a very long time for such a fast speed field, there has been lots of research on explainable and transparent AI. It's not black box anymore. And publish stuff so that you contribute to science. I have 2 more slides, bear with me. We have other projects in cancer specifically. For example, before even biopsy, you go to an MR, and from MR scans, we are trying to predict the Gleason score. So it's 3D data, so we use 3D neural net, convolutional nets, so 3D architectures. This is one interesting thing. We have even personalized AI models or machine learning models, because we take patients' background data into account. So your let's say medical history. So this can have better models, predictive models for you, personalized models, right? We are working with a huge hospital in Vietnam, in which we do the same 3D architectures to detect lung and locate lung cancer nodules. This is from CT scans. And we have partners in Chile and Turkey. So what is this pattern of developing countries rather than starting in developed countries like Finland? Because we waited more than 1 year to get that data from Helsinki University Hospital. The data was there. I'm talking about the administrative and ethical committee stuff. So these kind of developing countries, the regulations are less strict. So you have business advantage there to get the data. You have advantage of population. Imagine population of Vietnam. Everyone smokes. Everyone has, okay, many people have lung cancer. So data is the driver in this kind of, it's these kind of technologies. So you don't have to wait 2 years to get data from, let's say, local hospital here, but you have to start from somewhere because others are doing it. So we didn't wait. We are going in parallel in many fields, in many countries. And finally, if you are interested in hardcore machine learning job, come and talk to me. We are located in Helsinki. Thank you very much.
Any questions?
Yes, please. Bring it on. We started from the, let's say, 256 pixel, which is like the lowest you can actually, as a human, even. Yeah, yeah. Yeah. So we haven't fixed the zoom level, but we fixed the, we call it pixel level. So we decided to stay safe so that we can detect as zoomed in as possible, But then when pathologists usually don't work in that zoom level, as you told, because we are working with pathologists after all, so a couple of zoom out level, it can still detect, but we wanted to be safe that we can detect as zoomed in as possible that level. So which will enable, when you downscale the image, which is the same as going one zoom up. So that is covered in this solution, absolutely.
I was thinking that there are these solutions on many different kinds of things like this that they kind of like maybe do a separate model for different levels, and maybe like an average or something. But it would be interesting to somehow mix.
Yeah, that mixing mathematically is happening in the neural network model in a single neural network training in here, which we have different tile sizes, meaning zooms in a way. So we have a one model which can handle that. So we don't have this 10 different models for 10 zoom levels. In the architecture of the deep learning itself, we take care of that. Yeah, we did this whole exhaustive search for pre-trained inceptions and stuff, and that was kind of a benchmark. Inception ResNet version 2, I think that was the best model from the pre-trained ones, but then we did certain tricks on, we did our own architecture. So choosing between pre-trained models versus writing your own architecture, the most important aspect of this choice is your amount of data. If you don't have enough data, go with a pre-trained model and fine-tune it. If you have so much data like that, you have tens of hundreds of millions of tiles, you are better off with your own architecture. And in our architecture, we use certain tricks like some convolutional aware initialization, and so it's a bit, it performs a bit better than pre-trained models. But that a bit is statistically very significant because of the number of data. Yeah. Yeah. Exactly. So right now we have a solution for binary, as you said, and right now we are working on classifying as well. So this is an ongoing project, and that's what we are working on, as well as MR and other modalities.
The second data you have, is it for
Yeah. Yeah. That's true.
Question. When you did the annotation of the images here, did you build something for annotating it, or did you use some pre-made product?
The annotation tool we gave was open source tool.
So that was built by you?
No.
Okay, it was
No. Yeah. So we did just a bit of change on top of it to make it even easier for Windows user or whatever. So you have to have this like click, that's it level easiness in when you talk to doctors or anyone typically. Yeah.
Follow-up question about the inference. So you mentioned that, or did I hear you correctly? You deploy it inside microscopes, or
You can. We haven't done it yet. Yeah.
Currently, where do you deploy it?
So right now it is in the server.
Okay.
Yeah. So basically, if there's a new biopsy, pathologists like drags and drops to a folder. But if you have this kind of, we are now talking with Olympus and other scanners or microscope companies, which they want to have on the go, real time, right? So when you look at stuff, it will highlight. So that's the speed is of course an issue there. So you have to take care of. You have to maybe quantize your model or stuff like that too. Yeah.
Okay.
All right.
Any other questions? No. Okay, thank you.
Thank you.
Do you want to say something on behalf of Vadim?
Yeah,
Hmm? So please
Yeah,
come forward.
again, thank you. Thank you for our speakers. Thank you for organizing this meetup. It's amazing to see those enthusiastic people gathering about AI, especially my lovely Fredo. So I just wanted to thank you for attending and everything, and that's just very small things. So no advertisement or anything. I'm going to be here, and we have the Vaden people if you want to ask us anything about Vaden, why open source, what we are doing, how we're hiring, all these kind of things. If you want to stick around, have some pizza, drinks, the place is open. Otherwise, if you don't forget how we got there, there is a door